Hello, everyone, and welcome back to another episode of ZNotes Live. I'm your host, Yukan. I'm here with Malak, and today we'll be continuing with the Physics Past Year paper series, where we solve some papers from this year's May-June 2020 exam. In this episode, we will start with the AS level exams with the multiple choice paper, or paper 1-2. On to you, Malak.
Hello, everybody. So let's get on with it. Our first our AS paper. Is there something wrong with the...
Oh yeah, that's a bit...
Half the screen is not showing. How about now? Yep.
Oh, okay, that's better.
I fixed it. So, first question. What is a reasonable estimate of the mass of a raindrop? So, now we know the raindrop is extremely small. So, intuitively, you should know it's a really, really small mass. This here, the color's not really that obvious. This here is about 1 gram, which isn't really that small of a mass. We need something smaller. So just logically, it should be this one, the smallest mass that we have. Question 2. Which quantity is a scalar? Acceleration, force, kinetic energy, and momentum. So at this point in time, you should probably know that kinetic energy or any type of energy is always scalar. Of course, we know that acceleration is a vector and force is a vector because we always have force triangles and force vector triangles. So we should know by now. So it's kinetic energy. Question 3. A galvanometer of resistance 5 ohms is to be used in a null method. If you're not sure what a null method is, it's this to find out what the EMF of a battery is. In order to protect the galvanometer from damage due to an excessive initial current, resistors of resistance 0.5 ohm and 1 kilo ohm are available. Which arrangement would provide this protection? The 0.5 ohm resistor in series with the galvanometer. So in series, it wouldn't really give you that much protection because it's just adding 0.5 to the already existing resistance, which is not really helpful. 0.5 ohm resistor in parallel with the galvanometer, and this combination is placed in series with the 1K ohm resistor. So since the 0.5 resistor is placed in parallel, which means we have the resistor right here, and it's in parallel with the galvanometer, that means the galvanometer, their combined resistance right now is less than any one of them. So the combined resistance is less than this one and less than this one, right? So the resistance of both of them right now is very small. And then that is in series with a 1K ohm resistor. Now this would apply the best resistance because we basically have 1K resistance with a very small resistance on the other side. So we choose that option. Is that clear? Question 4. Readings are made of the current I for different voltages across a fixed resistor. The results are plotted on a graph to show the variation of I with V. All right? Which is the best description of the errors in the readings? Both systematic and random error. So random error is if you have random mistakes or random errors. So you'd have maybe 1 dot here, 1 dot here, and you don't know why. You can't tell why. Nothing is really, there's no pattern, you would say. But in here, you can see they're very precise or very accurate. Yeah, very precise, you could say, not accurate. Neither systematic nor random. No, so you know that in an IV graph, the line always runs by the origin. If there's 0 V, there is 0 resistance. If there's 0 resistance, there is 0. Right? So right now, it's not really running through the origin. So we know that it has to be systematic error. There's an error with the actual equipment that it's not giving us the reason. It's Okay, it's translated upwards. The whole graph is pushed upwards, which means we added a number. It's an error with the actual equipment. It's not random because it's all precise, it's all a straight line. And there is an error, so it's not this one. It has to be systematic error. Do you want to change anything or
No,
add
this is
anything?
fine.
A stone is dropped from a height of 20 meters above water. The graph shows the variation with time of the velocity v of the stone. So we have velocity time graph. Which statement describes the approximate position of the stone 4 seconds after it is dropped? So now here we have the time and we have the velocity. As we can tell, the velocity is increasing. We can tell this is above the water. And suddenly there's a drop in velocity as it enters the water. So you can tell this is the point where the stone enters the water. Now you can do this in two main ways. One way is shorter. Since you know this is when the stone dropped the water, you just calculate this area right here to find the distance below the water, which would be just simply 2 times 5. 2 is here, times 5, right? Which then we would have 10 meters below water, right? Now, if you didn't think of this in the exam, you can calculate the entire distance of the entire journey, this whole thing, and then subtract the distance above water. So if you do that, you would get 30 for the entire distance of the entire journey, minus 20, which is distance above water, and you get 10 below water. So distance is 10 meters below the surface of the water. Is that clear? A car X is traveling at a constant speed u along a straight road. At time t equals 0, a second car y is a distance d 0 behind car x. So now there's a car right here that's traveling at a constant speed. And there's a car right here that's traveling the distance d behind it. The speed v is less than the speed u. So now here, it's less. So if we write that down, we say v is less than u, right? At time 0, car y begins to accelerate with constant acceleration. So this car here is accelerating. Car y overtakes car x at time t equals capital T. All right? Now we know that when time equals t, they both reach the same distance. They're both in line with each other. Now we want to find the best graph. So this is the part. We know that this here, it used to travel with a slower speed at first, right? Which means this car the distance would have increased at first, as this car went ahead faster before this car started accelerating. And then when it starts accelerating, then the distance would slowly decrease. So suddenly, at first, the distance will increase and then decrease. So we know these two are not it, because it needs to have an increase up here first, as the distance increases first. Then we need to find out the rate the distance would decrease over here. This. Right? Now, as the acceleration is slowly increasing, it accelerates, which means the speed is increasing, which means the distance between them would become smaller and smaller at a constant rate. Not like this. This is that's a very, very big drop and then becomes very slow again. That's not how the rate goes. It's just very constant. So it is B, not A. Clear?
Yep.
The next one.
Yeah.
Question 7. The resultant force acting. Let me take this all off and then explain it on. Question 7. The resultant force acting on an object is slowly increase. Which graph could show the variation with the time t of the momentum p of the object? So now we know that this is a momentum time graph. and the force is slowly increased. So what equation do we have that links force, momentum, and time together? We have this famous equation. Force equals momentum over time. Difference in momentum over difference in time. So now we have here momentum on y and t on x. So we know the gradient is always difference in y over difference in x. So the gradient of each of these graphs is going to be equal to the force, right? So now, as we know, the force is increasing, which means the gradient is also increasing. So now we get to find out the gradient. The best way to do this is just draw lines along each graph. So in here, at first the gradient is going up, the gradient is high. Then slowly, the gradient is getting lower. It started off like this and ended up like this. So this is not what we want. Let's check out B. The gradient starts almost at 0. And slowly, the gradient increases. It started off like this and it ended up like this. The gradient increased. So it's B. If you check the rest, you would find the same with each one. The gradient would start out big and then end up small. And this here in D, the gradient is constant all throughout. Now here, G decreases, G decreases, and G increases. Is that clear? So in this one, don't care too much about where the line is pointing, care about the gradient. How steep does the gradient look? Because the gradient is equal to the force. Doesn't matter where it's actually pointing.
Yeah.
Next one.
Yeah, I would like to add something as well. Yeah, like Malak said, do ignore where it's pointing, even though in the first one the line is increasing and in B the line is decreasing. Just remember that momentum is a vector quantity because it is mass multiplied by velocity. So it can go in either directions, and like, how do I say it? Well, a force can be applied in any direction, and the momentum decreasing or increasing would be like, it would make sense still.
What matters is that how much the F is increasing, and
Yeah.
F is just the gradient right now, mathematically. So we just want the steeper gradient. Next question. 8. An astronaut has a weight of 660 newtons when she is standing on Earth's surface. The acceleration of free fall on the surface of Mars is 3.71 meters per second square. What would be the weight of the astronaut if she stood on the surface of Mars? So now it's a simple matter of us finding the mass of the astronaut and then multiplying it with the acceleration of free fall on the surface that she wants, which is Mars at this point. So for finding the mass, we just divide the force by the acceleration of free fall on Earth. So it's because right now she's standing on Earth, we need to find her mass. So we know the acceleration of free fall is 9.81. It's given to you in the front of the paper. We divide them, you get the mass, and then you find the weight on Mars by multiplying the mass with the acceleration of free fall on Mars. And you get an answer. You should approximate it or do whatever they, round it. Yes, you should round it until for the nearest answer, which you have in the choices. Question 9. A mass m1 traveling with a speed u1 collides with a mass m2 traveling with a speed u2 in the same direction. After the collision, mass m1 has speed v1 and mass m2 has speed v2 in the same direction. The collision is perfectly elastic. So here's a diagram to help you out understanding it if you got confused reading the question. Everything is just showing here. Now, there's a very important point here. The collision is perfectly elastic. Now, of course, we know some rules about elastic collisions. Well, one is that total kinetic energy is conserved. Total kinetic energy before is equal to the total kinetic energy after. Second is relative speed of approach is equal to the relative speed of separation. And the last, which applies to all collisions, is total momentum before is equal to total momentum after. Now, these are the three rules we have. Now to check which equation is not correct. The first one, we can apply the law of kinetic energy on it. Since we have square here, you could tell that it's made by the law of kinetic energy. If you try to write it down and check and rearrange the equation around, you would get the same equation, which is m1 u1 square minus m1 v1 square is equal to m2 v2 square minus m2 u2 square. So this one here is correct due to this law. Second one is relative speed of approach is equal to relative speed of separation, which means if we take u1 minus u2 should be equal to v2 minus v1. Again, play around with the equation and you should get b. So b is true, again, due to the second equation. 3. Total momentum before is equal to total momentum after. Of course, we all know this. Again, just play around with the equation m1u1 plus m2u2 equals m1v1 plus m2v2. Play around with it, and you should get same as equation C. So we know this is true due to the third law. So now the only one we have is D. So that is the only one that is not correct. Is that clear?
Mm-hmm. Yeah.
The diagram shows a negative electric charge situated in a uniform electric field and a mass situated in a uniform gravitational field. So now, of course, since this is pointing to the right, we know that it's going from positive to negative. So we can just write that down here for just reference to know where's the positive side, where's the negative side. And as for the mass, you know it's attracted to the larger mass. You don't need to draw this, I'm just doing it for reference. Now, which row shows the direction of the forces acting on the charge and on the mass? Well, we can first start with the mass. Since this is a gravitational field, the mass will just be attracted with the in the same direction as the gravitational field. So it will be going to the right. So we know that these two are wrong, since the gravity is to the right. Now for the charge, as we know that this here is positive and this here is negative, a negative charge is be attracted to the positive side. So it would go to the opposite direction of the force, which would mean B. Is that clear?
Yep.
Question 11. A bicycle pedal is connected to a pivot by a metal bar as shown. The force on the pedal is 60 newtons downwards. What is the moment of this force about the pivot? All right, so now first off, moment is equal to force times perpendicular distance. Distance needs to be perpendicular from the pivot, right? So now there's two ways to do this. One is to, since this force is acting downwards, is to find the component that is perpendicular to the pivot, right? When you do that, you find this right here. You want to find theta, then you find x, and you try and find the component this way. But this is, again, a multiple choice question. Why go through all that trouble? They already gave you 16 centimeters, which is the perpendicular distance from the pivot to the force. So if you just take 16 and multiply it with 60, you would get the same answer as the complicated way. So this way you could probably do in a theory exam, because they wouldn't give you this in the theory exam. They want you to find all the component of forces and find if the force was this way, what's the component of it for it to be perpendicular to the pivot or the bar. But you don't need to do that here. They already gave you the distance that is perpendicular. So just multiply 60, which is the force, to the distance, which again, turn to meter. That is important. And you would get the answer. Clear?
Yep.
So if in the exam they give you right away, you don't have to think about it more. Just take the number that they give you that's perpendicular and slap it into the equation. A thin horizontal beam XY is freely hinged at point Y to a vertical wall. The beam is held stationary by cable ZX, XZ, which is attached to the wall at point Z. So you have a diagram here again, if the writing confused you. The beam supports a weight W at point X. The forces in the cable and in the beam are Fc and Fb respectively. Which vector triangle represents the forces acting on point X? So now the first thing you should notice here is that the beam is in equilibrium, right? Which means the net force is equal to 0, right? Which means we want a closed triangle. There is no resultant force. The net force is 0, so we want a closed triangle. For example, everything either pointing clockwise or anti-clockwise, right? We don't want a resultant force again. So now we should just check very quickly for the triangles that we have, which triangles are closed, which triangles are not. So this here, as we know, this is closed. It is pointing anti-clockwise. This triangle here, these two are pointing in the same direction, but then this points in opposite direction. So we know that it's not a closed triangle. This one here, same, not a closed triangle. This here is another closed triangle, right? So now it can be either this or this. Now we should check the weight. If you've noticed here, for some reason, the weight is pointing upwards. Now, as we know from our personal experiences in the world living, weight is normally pointing downwards. So we know it's A and not D. Question 13. A pipe open at one end floats in a liquid as shown. The cross-sectional area of the pipe is 0.012 meters square. The weight of the pipe is 32 newtons. What is the density of the liquid? So, now first off, we know that the pipe is floating, right? Which means the pressure downwards is equal to the pressure going upwards. Correct? Now, we know that the pressure, this one here, pressure pipe, PP, is F over A, because we know that the force, which is the weight of the object, which we have right here, and the cross-sectional area. We have both. So we can calculate the pressure of the pipe, force over area. As for the pressure of the water, which would be rho GH, the equation that we have. Now we can, since they're both equal to each other, we can have these two equations and intertwine them. Just P equal P. So then we know F over A is equal to rho GH. We write that down. And then we isolate rho in one side. So then we get this equation. Rho equals F over AGH. We plug in the numbers that we have, and we get rho, which would be B. Is that clear?
Yep.
Question 10.
Also, I would like to add, sorry, could you go back? They gave a length 0.4 meters that you do not need to use in this. So some people, whenever they see something that isn't used in the formulas that they're given, they might redo their calculations just to include that formula. But just remember, sometimes things are there and you don't need to use them. So in this case, the H, the only length that you need is the length from the surface of the water to the bottom of the pipe. That's all you need. So you can ignore like the other length given.
That will actually be relevant in many more questions later on. They're really confusing because you think you need all the information they give you when you just need one or two. During an interval of time, fuel supplies energy X to a car. Some of this energy is converted to kinetic energy as the car accelerates. So this here is the energy we want. It's the useful energy. The rest of the energy Y is lost as thermal energy. What is the efficiency of the car? So efficiency of the car is useful energy over total energy. Correct? Now we know the Y is the lost and X is total. So useful would be the total minus lost. So X minus Y, which is useful. And then over total, which is X. So X minus Y over X. that clear? And we get C. In which situation is work done on an object? So first off, very quickly, work done is force times distance. So we need a net force and we need a distance moved. The object slides with a constant velocity along a horizontal frictionless surface in a vacuum. So first off, constant velocity, which means we know that net force is equal to 0, which again means no work is done. A person holds the object at arm's length and at a fixed height above the ground. So there's no distance moving, there is no work done. A person pushes the object up a frictionless ramp. So we know a person is pushing and something is moving. So there's force being applied and there's distance moving. Therefore, work is being done. Move to the next question. A spring is attached at one end to a fixed point. A mass is then hung from the other end of the spring. The spring has extension x when the system is in equilibrium. All right. Now, first thing we need to know is that the gradient of this graph is k, and the area under the graph is work done. So the area would be here, would be the work done. And since this is a square, this area here, A, would be equal to this area here, B. So this area here would be equal to this area here. Since this is a square, this is not normal for all graphs, only because in this situation right here, it's a square. That is the only reason. So in this case, the area SQR, right here, SQR is equal to area SPR. So the variation of tension in the spring with this extension is shown on the graph. Which statement is correct? Area SPR represents the energy stored in the spring, which cannot be recovered. So the first part of this choice, which is here, is correct. Area SPR does actually represent the energy stored in the spring, but it can be recovered because right now it's a spring that follows Hooke's law. It has not yet reached any point of plastic deformation. It still would recover after the mass is gone. So the first part of this answer is correct, but the second part is wrong. Area SPQR represents the energy stored in the spring, which can be recovered. So area SPQR would represent SPQR would be equal to 2SQR, which, no, that's not what we want. SQR is the energy stored. So that's not correct. Area SPQ represents the loss of gravitational potential energy of the mass due to the extension of the spring. No, we have nothing right now, as of now, to link gravitational potential energy to the elastic energy of the spring. As of now, we don't have any equations that link those two, so we have nothing to back that up. G. The area SQR represents the elastic potential energy stored in the spring. Area SQR, right here, SQR represents the elastic potential energy stored in the string. That answer is correct because the area under the graph is the work done, therefore the energy. Anything you'd like to
add? Nope.
Question 17. An escalator in an underground station has 25 people standing on it and is moving with a speed of 4.3 meters per second. The average mass of a person is 78 kilograms. And the angle of the escalator to the horizontal is 40 degrees. So I drew a little diagram here to make it obvious. We have the triangle and the angle is 40 degrees. The weight is acting downwards, and this is what we have here. Now the escalator is moving the people with a speed of 4.3. We want to know the power. So we have the equation of power right here. Power equals E over time, which means energy over time. Now, the energy that's being used right now is we're making the people go up. So the height, there's a height difference, and the escalator is pushing people upwards. So we can use mgh, correct? Now, mgh over t. H over t would be the speed, because distance over time. And then mg is the weight. So now we have the equation of W. Let me write that down as well. Now the equation of also W times V, right, which is also equal to power. Now, here's the part, right? The thing is, where W is acting downwards, right? But the speed is in this direction. So let's make W also in this direction. Make it all on this axis right here, on the same line. So we need to find out this angle right here and find the component of W along this axis. True? All right.
Yep.
Now we have this triangle right here, which has a 40, and there's a right angle here. You can find the angle of 50. This angle here, which we find is 50. And then do W cosine 50, which is this side right here. Or if you can just tell right away, just intuitively, that this is sine 40. But if you can't, it's okay. You can still find this angle right here. So it's either W cosine 50 or W sine 40. Both would give you the same answer. So P, which is power, would be mg sine 40 times V. mg is, of course, W. You plug in all your information in here, and you would get the answer of 53 kilowatts, which is C. Clear?
Yep.
All right, this question. An elastic cord of unstretched total 16 centimeters and cross-sectional area 2 times 10 power minus 6 meters square is held horizontally by two smooth pins a distance of 8 centimeters apart. So they're just telling you that they've made it 8 centimeters apart. The cord obeys Hooke's law. A load of mass 0.4 kilograms is suspended centrally on the cord. The angle between the two sides of the cord supporting the load is 60 degrees. All right? So right now, simply we have a cord that's 16 centimeters, unstretched. And we put two pins here. And this is how it looks. We put a mass over this side, and it made this equilateral triangle with the angle 60. Now, we need to find the Young modulus. Now, the equation of Young modulus is E equal to stress over strain, right here. And then you can break it up even more to E equal F times L over A times extension. Now, we have A and L, right? So we need to find extension and F. Extension would be easy. You can find it out pretty easily. F will be the tricky part. So now we need to find the force acting on the cord. We need to realize that the only force acting on the cord is tension along these two lines. This is a diagram right here to break it up even more. And that this diagram right here is in equilibrium. Nothing is moving. It's at this point, which means the force down is equal to the force up. The force down is weight. So force up is equal to mg, which is the force down. And that these two here, the tension of these two lines, have an upper or vertical component. When they add up, they make F up. So the vertical component of T1 plus the vertical component of this one would create the force up. So now they have these two equations. We have F up equals mg, and F up equals 2 cosine theta, which we know theta is 30. Now we can combine these two equations. Up here, we have mg equals 2t cosine theta, right? We, again, isolate t to one side. We would get T equals mg over 2 cosine theta. And we have the force of tension right here. Now, as for extension, we know this is an equilateral triangle, so we can tell that all sides are the same length. This is 8 centimeters, 8 centimeters, 8 centimeters. So the total length of the stretched chord is 24 centimeters, and the length of the unstretched chord is 16. You subtract them, and you get the extension, which is 8 centimeter. Some people can just tell this intuitively, but I prefer writing it in equation form, just so people know where it actually came from. Now we know the extension, and we just plug in all the numbers that we have into the equation, as in the force, which I wrote here as T to make more sense. You write the tension, length, area, and extension. Now, one more thing you need to make sure that you do correctly. Since they made the area in meters, you need to write these two as meters as well. So you plug in all your numbers while making sure that you converted all the units to meters, and you would get the answer 2.3 times 10 power 6, which is C. Everything clear?
Yep.
Question 19. A student is investigating the mechanical properties of a metal. He applies different loads to a long, thin wire up to its breaking point and measures the extension of the wire for each load. He then plots a graph of stress against strain. The student repeats the experiment with a wire made from the same material with twice the original length and half the diameter. Which graph is obtained? Now, the first thing very important point is that it's the same material, right? And the Young modulus, E, is a property of the material, right? So is a property of the material. All right? Which means it doesn't matter what change you make to the length, what change you make to the diameter. As long as it's the same material, it would have the same Young modulus. And Young modulus is equal to stress over strain, which means the gradient of this graph right here is the Young modulus. So no matter what we do, we need to have the same gradient. So over here, this here has the length increased, but this here has the same graph with the maximum stress 4 and the maximum strain 40 and the same shape. So this would be the answer, since it wouldn't have an effect on the Young modulus for the known values that we have.
Yep.
Clear? So very quickly, don't get confused and accidentally double the length and the stress. Same material means same Young modulus, same breaking point, no difference. Which statement describes what is meant by the plastic deformation of the material? So plastic deformation is when you have a force extension graph, it would have a straight line area, which is the elastic change or elastic change. But then after that point, there's a breaking point here where it no longer follows Hooke's law. And here you would call it plastic deformation, where as soon as you take off the mass, it would not return back to its normal length. A, it always obeys Hooke's law. Nope, that is an elastic deformation. It does not return to its original length when the extending force is removed. Now this here is a plastic deformation, because if we remove the mass from this point, it will not return back to the original. Next question. Question 21. A transverse wave is moving along a rope. 2 points, x and y, on the rope are a quarter of a wavelength apart from each other. Which statement is not possible for the 2 points, x and y, at any instant? So 1 point is that it's moving, so it's a progressive wave. Which means that no point on the wave is ever stationary. It's not a stationary wave. All points are moving, always. Which means they're both stationary. No, that's not possible. Not even one of them can be stationary at any point. So A is wrong. And they want the not possible. Question 22. Two progressive waves meet at a fixed point, P. The variation with time of the displacement of each wave at point P is shown in the graph. So we have the graph here. And what is the phase difference between the 2 points at point P? So to find the phase difference, you need to find the distance between 2 points, two same points on the two different waves. So for example, right now this wave is going downwards right here, and this wave right here is also going downwards. So these 2 points are the same on both waves. Find the difference in time between them, and then find the period of one wave. Now these two waves have to have the same period for this equation to apply. So for the phase difference, you would find the difference in time between the two waves and the period of one wave. You plug them in, multiply them by 360, and you would get this right here. You should know this equation. If you don't, you can just think of how if two waves are exactly 180 degrees apart, that means like 1 over 2, 360, which equals to 180. So the difference between them would be half. This t here would be half the t here. That's what I remember here to remember this equation right here.
I see.
Next. Question 23. A microphone connected to the Y plate of a cathode ray oscilloscope, CRO, is placed in front of a loudspeaker. The trace on the screen of the CRO is shown. The time-based setting is 0.5 meters second per centimeter, and the Y plate sensitivity is 0.2 millivolt per centimeter. What is the frequency of the sound from the loudspeaker, and what is the amplitude of the trace on the CRO? Now, it's just a simple matter of counting and multiplying. Right now, we have for the frequency, first we need to find the time period, which means the difference in time, how long it takes to get for one wave. So 2 points the same, you count how many squares, which was 6 squares, and then you multiply by the time-based setting right here. So 6 times 0.5 times 10 power 3, and you get the time period. Frequency is 1 over time period, which I got 330. So it can't be this, and it can't be this. It can't be C or D. Now, as for the amplitude, you just check how much displacement from the base, and we got 3 boxes. So we just now multiply 3 by the plate sensitivity on the y-axis, and we get 0.6 millivolts, and that is the one here. Again, it's just a matter of multiplying. Next question.
Yep.
Question 24. The diagram shows an experiment to produce a stationary wave in an air column. A tuning fork placed above the column vibrates and produces a sound wave. The length of the air column can be varied by altering the volume of the water in the tube. Okay, so the tube is filled and then water is allowed to run out of it. The first 2 stationary waves occur when the air column lengths are 0.1 meter and 0.42 meter. What is the wavelength of the sound? So first off, you can do it in 2 ways. One method is that since it's the same first one, this is the second one, you can subtract them, and when you subtract them, you would get half a wavelength. Right? And then you could find the length of a wavelength using that. Or when the first stationary wave is made, you know this is quarter of a wavelength, and right away you just multiply 4 by this length. Clear? This is the shortest method. I suggest you use this one. This is just same thing but longer.
Also, I can add that if you add just 0.14 and 0.42, you also get 0.56. And it's not a coincidence, because you know that the first stationary waves occurs at quarter wavelength, and then the next one at half, and then the next one, you can just add them and then you'd get one full wave.
That is also a different method, yes. Question 25. A stationary person measures the speed of a wavelength of the sound from a horn on a stationary vehicle. The person then repeats the measurements when the vehicle is approaching at a constant speed. Which row describes the measured wavelength and the measured speed of the sound wave from the moving vehicle when compared to the sound wave from the stationary vehicle? So right now we measure the wavelength and speed. So this is when they're both stationary. This is when it's moving. Right? Now, when they're both stationary, you know that it's just a normal wavelength. But when it's moving, you know the wavelength as the car is approaching you, the wavelength now becomes, you can say the waves become squashed. So the wavelength is shorter. As for the speed of sound, it's always the same as long as the medium is the same. The speed does not get affected. It's the wavelength and the frequency. So the speed never gets greater or shorter. It just stays the same. So we have D that complies with these 2 points. Question 26. The table shows the wavelength of electromagnetic waves. Which row correctly identifies the principal radiation for each of these wavelengths? So now you can try and memorize each of the electromagnetic waves. What I do personally is that I memorize the order. So RMIVUXG. You can find a sentence that uses the first letter of each of them as one sentence to make it easier. And then I basically just memorize the visual light, radio wave, and gamma rays. So visualized is always -7, 10 power -7. Radio waves are the biggest. They have 10 power. They can get to 10 power 6. And gamma rays are the smallest. They get to 10 power minus 16. Right? So now when we get here, you can use these 3 guidelines right here. We have these 3 guidelines right here. You can use them to try and find out which one's right placement. So first off, I can see here, where is it? 10 power 6, 10 minus 6. Wait. First off, you gotta check with the radio and gamma, because they're smallest and biggest. So since we have 10 power 2, which is really big, it's not even have minus meters, it has to be radio wave, which means we cross these 2 out, because it has to be radio waves. Now we only have 2 options, A or D. Now we can check if there's gamma rays. -16, -14. These are very close. So this one has to be gamma rays. So it has to be question A. So I try and do them this way. I only get 3, the middle, the biggest one and the smallest one, and try to have everything related to that. That way you don't have to memorize every single one of them or every single range. Let me erase this mess.
Another way you can do it is, let's say you don't memorize the wavelength of each individual one, you just remember the order, then you can just check that it goes in decreasing order. For example, the one in D, it goes from X-ray to infrared to ultraviolet. That is a high energy ray to a low energy ray and back to a high energy ray, even though the wavelengths are continuously getting bigger. So that doesn't make sense. The only one that follows the order is A.
Yes, that is also a faster way to do it. So just try and memorize this. You can look up on the internet for any sentences that help you memorize them, or just memorize them straight on. Which two progressive waves meet at a point? Which condition must be met for superposition of the waves to occur? The waves must be coherent. No, they don't have to be. It can be a wave with very high frequency and a wave with very low frequency, and they can still both interfere with each other. The wave must be the same type. That is true. You cannot have water waves interfere with sound wave. That does not make sense. They both need to be of the same type, which means B is the correct answer. On to the next question. 28. A hell separates... Ow. The hair got stuck in my glasses. A hell separates a television, TV transmitter from a house. The transmitter cannot be seen from the house. However, the house has good TV reception. By which effect at the hill could the TV signal reach the house? So now we have the TV transmitter here, and it somehow bends up and goes down here. Now, the bending of electromagnetic waves is called diffraction. So we know
Mm-hmm.
it is B. As it did not go on a straight line, it bent. That is called diffraction.
Mm.
29. Diagram shows an arrangement for demonstrating two-source interference using coherent light. Coherent light of a single wavelength lambda. Okay? An interference pattern is observed on a screen 3 meters away from the slits X and Y, which have a separation of 1 millimeter. Okay? Central bright fringe is at Q and the second bright fringe is from the center P. What is the distance between P and Q? So we have to find out this right here. Right? So first off, we know the equation lambda equals AX over D. So X is between Q and this right here. We want 2X, which means from P to Q. Right? And we also
Mm-hmm.
have all the information available to us. The only tricky thing you need to focus on is that it's 2x. We multiply everything by 2. So now we do 2 lambda d over a. Put in all the numbers you have, and you would get 6 times 10 power 3. This is a problem with the actual question paper. This is supposed to be power 3, not 103.
Ah.
Yeah. Question 30. The light of wavelength lambda is incident normal on a diffraction grating. The angle between the second order maximum, so now we know that n is equal to 2, and the normal to the grating is theta. The variation with sine theta and lambda is shown on the graph. So now we have over here is lambda, and over here is sine theta. So now we know the equation. We know, of course, the equation d sine theta equals n lambda. So if we isolate d equals n lambda over sine theta, right?
Mm-hmm.
Now, if you've noticed here, lambda is in the y, sine theta is in the x. So lambda over sine theta is equal to the gradient, correct? So if we multiply n to the gradient, we get d. The gradient, we find the gradient, which is 1.25 times 10 power minus 6. And from that, we find d. There we go. Correct?
Mm-hmm.
Now,
Yep.
we want to find the number of lines per millimeter are on the diffraction grating, right? So now here, d is in meters, right? So to find number of lines, we do 1 over d. But since we want them in millimeters, we do times 10 power minus 3, right?
Mm.
So n equals 1 over d times 10 power minus 3. And we get 400 lines per millimeter, which is A.
Mm.
Clear? Question 31. A dipole is a pair of charges of equal magnitude, one negative and one positive. The electric field of a dipole is shown below. In which direction does the force act on an electron when at point X? So electron, we know it's attracted to the positive and goes to the opposite direction of the field. Right now, at this point right here, the field's pointing this way. So it
Mm-hmm.
would be going to this direction, D.
Mm.
Some people might do C, as in it's attracted to the positive, but no, it's just in the opposite direction to the force or to the field lines.
Mm.
So it's going at D since the force is this way.
Yep.
Question 32. A charged oil droplet of mass m is falling initially freely in a vacuum between two horizontal metal plates that are separated by a distance x. So there you go, we have this right here. The potential difference PD is then applied across the plates. This results in the oil droplet continuing to accelerate downwards but at a reduced acceleration. The polarity of the applied PD is then reversed, so the direction of the electric force on the droplet is reversed This results in a downwards acceleration of the oil droplet increasing to 3a. What is the magnitude of the charge on the oil droplet? So right now we have a lot of information. They give us a lot, and it's really confusing. I actually decided to try and solve this with you instead of having it pre-solved, because then it's really a big mess. Now, first off, we have this right here, right? At first, it said that it's going downwards at G. There's nothing, there is no force happening, right? So the downwards acceleration is G. Then they tried it again. Let me do a bigger. Then they tried it again. Same distance, x, right? But this time, the downwards acceleration G, and there's also an upwards force F, right? Because this time there is right here, and this here will be positive, this here will be negative. And this is a negatively charged, so it would be going upwards. So acceleration is A, which is less than G. Then they did it a third time, where they flipped the battery, right? We have it again here. We have the droplet here, M. We have G right here, right? This time we have here negative and here positive, which means there's a force going downwards, right? This is all the information they gave us. But now we know that the charge, this is the part where, like Yukan mentioned earlier, not all the information they give us is important. We know that the charge is a property of the actual oil droplet, of the charges in it, right? So all of this here can be all information to confuse you, right? Now let's assume that there is a third one right here, where the droplet is at equilibrium. So the force upwards is equal to the G downwards, or the weight downwards, right? And there is right here, like earlier, so there's a force over here that's upwards and equal to the weight downwards, right? So the droplet is at equilibrium. This means right now that F, let's call this right here F, E. This means that Fe is equal to W, correct? And that, let me erase all of this here, because we don't need it. Actually, let's keep the top one. Fe is equal to W, right? Which means Fe is equal to mg, right? Now, Fe is also equal to the energy on it. So the energy of the actual, the force of field. So the force of field, which is EQ. EQ is equal to mg, right? Now, EQ, we have two equations on it, because EQ, right here, let me explain this more. We know that E is equal to F over Q, right? So F is equal to EQ, right? And we also know that E is equal to V over D, right? So now here we can have V over, since they called dx, well, write Vx, Q equals mg, right? And now G we know is acceleration, so we can call it, G we know is acceleration, so we can call it A, acceleration of free fall, right? And now we need to isolate Q to one side, so it would be Q equals max over V. So The point here is that charge is a property of the oil drop. It doesn't matter if we reverse the battery, it doesn't matter what any of the information they gave us earlier. What matters is that we want to find
Hmm.
Q. So what we try and do is that we try and rid ourselves of all this confusion and try to create a scenario where the drop is at equilibrium. And then from there we find the charge of the actual oil droplet.
Mm-hmm.
Clear?
Yeah. An alternative way you can do this is just by looking at the second one. They already gave you an acceleration A, and you know that the force is due to the field. So ma equals to E, and then you can just use the information that you no F equals to ma, and then you can use your information with the field strength that E equals to F over Q and E equals to V over D. So using that, you can eliminate F and you can eliminate E to get your final
Mhm.
equation max over V. But yeah,
Yes.
you'll get the same thing.
Mhm. Question 33. The number density of free electrons in copper is 8 times 10 power 28 meters per meter cubed. A copper wire has diameter of 0.42 millimeters. What is the average drift speed of the free electrons in the wire when the current in the wire is 0.57 ampere? So we have the equation, of course, I equals NAVE. E is the charge of the electron. I like to write E instead of Q, so because then it has the word nave, it's easier to remember. So E, they give it to you in the beginning of the paper. You don't have to memorize it. As for A, since the wire is probably a cylinder, so you can just find the area since they gave you the diameter, right? So the area is
Mm.
pi r square. Remember r, not diameter, so over 2, and this is also millimeter, you turn it to meter. So multiply by 10 power 3 to make it a meter, and divide by 2 to have it be radius, not a diameter. And square that to get the area. You don't have to do this, you don't have to get confused, just put it on the calculator. And then also just rearrange this, isolate V, and then you would get V equals I over NAE. You plug in all your numbers and you get answer D.
Mm-hmm.
An electric kettle is rated at 2 kilowatt, which describes the power supplied to the heating coil in the kettle. The coil has a resistance of 5 kilowatt. What is the current in the coil? So you have the equation, the base equation, P equals VI, which then equals I square R. So P equals I square R. We isolate I on this side right here, and we get I equals square root P over R. You plug in your numbers,
Mm-hmm.
and you get the answer B.
Mm-hmm.
Question 35. A conductor consists of 3 wires connected in series. The wires are all made of the same metal, but have different cross-section areas. There is a current I in the conductor. Okay? Point Y on the conductor is at zero potential. So here there is zero potential. We know that needs 0 at Y. Which graph best shows the variation of the potential V with the distance along the conductor? So we have 3 areas on this, area A, area B, and area C, correct? Now, since
Mm-hmm.
in here we have the biggest area, we would have the smallest change in the PD, smallest loss in the voltage, correct? And then in here, there would be more of a loss, more loss, and here we'd have most
Mm-hmm.
loss in V. Correct? So now we
Mm.
check the graph that we have. In here, we could see that the loss is this is a loss in area A. Then this is a loss in area B. This is a loss in area C.
Mm.
So as we can see, the loss is getting bigger. It's losing in area A. It's losing potential difference, losing potential in area A, then losing more potential in area B, and the most in area C. When we get to B, it's losing the most in area A, if you could see here, then loses less in area B, and loses the least in area C, which is incorrect. As for C and D, there is no loss while it's in area A, but then suddenly there's a loss, which as if it suddenly lost all the PD here. No, it loses the PD gradually as it's moving across the conductor. So A is the most tutored. Here. Anything you'd like to add?
Yep. No, this is all fine.
Question 36. A cell of electromotive force EMF E and internal resistance 0.5 ohm is connected to a resistor of resistance 4.7 ohm. All right. The maximum power that can be dissipated by the resistor without overheating is 0.5 watts. What is the maximum value of E for the resistor not to overheat? So right now, we just want to find electromotive force while taking account of internal resistance. So you know the equation, E is equal to VR, which is the resistance outside, times VR, the potential difference lost inside, right? So again, we divide that into I big R, I small r, but we don't have I right now through the numbers they gave us. So to find I, we use the power. They give us the power right here. So P is equal to IR squared. We find I, and we plug that into the equation. And we get the answer C. Clear?
Yep.
Question 37. Christoph's first and second law link the conservation of physical quantities. Which quantities do they link to? So the first law says that the sum of currents into a junction is equal to the sum of currents out of the conjunction. Current is basically charge per second, which means it is a law of conservation of charge. The sum of charges into is equal to the sum of charges out of. As for second law, which states the sum of EMFs in a closed system is equal to the sum of PDs across the circuit, and which means the energy gas given to the circuit is equal to the energy lost in the circuit. This shows the law of conservation of energy. So the answer is A. Question 38. The circuit shown, X is a variable resistor whose resistance can be changed from 5 ohm to 500 ohm. The electromotive force EMF of the battery is 12 volts. It has negligible internal resistance. What is the maximum range of values of potential differences across the output? So now the equation is V out is R2, which is right here, over R1 plus R2. This is R1, this is R2, times Vn. So now for the minimum, V out minimum, we take the minimum resistance and we just plug that in, 5 over 5 plus 40 times 12, and we get 1.3 as the minimum. For the maximum, we just take the maximum value of resistance, plug that in, and we get 1.1 volts. So the range we would have is from 1.3 to 11.1. Next question, 39. An unstable nucleus goes through successive decay and becomes a final stable nucleus. The initial nucleus and the final nucleus are isotopes of each other. How many alpha and beta particles could have been emitted during the decay sequence? So for two nucleuses to be isotopes, we would have the same atomic number, but it's okay if we have different mass numbers. And for the alpha decay, we lose 2 from the atomic number and 4 from the atomic mass. For the beta, we get 1 from the one extra atomic number. So for them to be both isotopes, we would lose 2. We would need the A to be the same. So if we lose 2 from the alpha decay, we would need to gain 2 from the beta decay. So we would need 1 alpha decay plus 2 minus 1 beta decay, right? So let's say, for example, we have particle X with mass M and atomic number A. It undergoes this decay. So then we would get here, let's say, X with the mass M minus 4, because we have beta right here. And then we would have minus 2 plus 2 plus 1 plus 1, which we would get still A. More specifically, we get A minus 2
Yep.
plus 1 plus 1. So we need 1 alpha and 2 beta. Last question.
Yep.
A hadron has a charge of E minus and is composed of 3 quarks. E minus is a charge of minus 1, which is a charge of electron. What could be the quark composition of the hadron? So we have up quarks and strange quarks. We know the up quarks are plus 2 over 3 and strange are minus 1 over 3. So in here we have 3 strange. So if we have, it's like we have 1 over 3 times 3 and we get minus 1. So it's strange. And that brings us to the end of question. That's the end of paper 12, multiple choice AS level. That was a very, I would say, a very tricky paper for AS level.
Yep.
It had a lot of
Is there
tricky
any
questions.
advice that you'd like to give for students?
I would say that if a question takes you more than 2 minutes, go to the next one, because you don't want to waste time on it. And then after you finish the entire exam, and you would still have time, then go to the other questions that would take you time and spend your time on them. Because if you waste all your time on a single question, it's only going to give you 1 mark, and then you accidentally miss 10 questions because of the time. Because this paper is all about time, and some questions take a lot of time. So if a question takes you some time, skip it, remember what question that was, and then come back in the end and try and answer it.
So definitely whenever you guys are looking at any MCQ paper, time is a very big factor. And although our live stream took about 1 hour and 12 minutes to finish the paper, that was all because Malak was trying to introduce concepts and explain ideas that she used to solve this paper. When you're actually doing the paper, of course, this thought process should come in a sequence to yourself, and you don't have to explain it to someone. So it would be a lot faster. And yeah, that is the end of our session for today.
Yes.
I hope all of you enjoyed this session and learned something valuable. Thank you, Malak, for taking your time to do this session. Please follow our social media shown on the next slide. All links are in the description. Enjoy the rest of your day and good night.